Assalamualaikum. My name is Norshaza Amira. My metric number is S62318. Today I will present about locality of different programs, Project 1, Set B. For the introduction, for a specific time period, a computer program tends to access the same set of memory locations, which is known as locality of reference. In the other terms, locality of reference refers to the computer program's proclivity to retrieve instructions with addresses that are close together. There are many types of locality. First is temporal locality. Temporal locality means that the data or instruction being received may be used later. Therefore, we should save the data or instruction in the cache memory to prevent having to search it for again in main memory. Second is spatial locality. Spatial locality means the processor may need to fetch the instruction or data from memory quickly. Unlike temporal locality, we are expecting that the data instruction will be needed soon. With temporal locality, we mean the memory location being fetched. Next is memory locality. Memory is explicitly used by spatial locality in memory locality. The last one is branch locality. If the spatial-temporal coordinate space has just a few feasible alternatives to the possible part of the past. The importance of locality. First, locality in programs has a significant influence on the design and performance of hardware and software systems. Second is, virtual address space part can be stored in the main memory of operating system, as well as recently used disk blocks on this file system, according to the locality theory. The last one is the application programs like web browsers use temporary positioning to cache recently referenced documents on a local disk. In the first task, we need to obtain the miss rate of NASA 7, SWM, and MDLJD. First thing first, we need to set up our SMP cache with the following architectural characteristic that given in the question, which is processor in SMP is equal to 1. Cache coherent protocol is equal to MESI. Scheme for bus arbitration is equal to random. Worldwide is equal to 16 bits. Words by block is equal to 16. Blocks in main memory is equal to 8192. Blocks in cache is equal to 128. Mapping is equal to fully associative, and the last one is replacement policy is equal to LRU. For MDLJD, in figure 2.1 shows a graph for MDLJD cache evolution. It shows that hit rate is increasing while miss rate is decreasing. In main memory block, it shows that miss rate is increasing and remain unchanged while miss rate is decreasing. In multiprocessor evolution, it shows that hit rate is increasing while miss rate is decreasing. Second is NASA 7. For NASA 7 in cache evolution, it shows that hit rate is increasing while miss rate is decreasing. In main memory block evolution, it shows that no activity in this evolution. In multiprocessor evolution, it shows that the hit rate is increasing while miss rate is decreasing. And the last one is SWM. For in cache evolution, it shows that hit rate is increasing while miss rate is decreasing. In main memory block evolution, it shows that hit rate is increasing and remain unchanged, then decrease a little bit while miss rate is decreasing and remain unchanged, then increase a little bit. And in multiprocessor evolution, it shows that hit rate is increasing while miss rate is decreasing.
Hello guys, my name is Abdul Kadir and I will present about the discussion of the project. First, we can go through to the question first. Do all the programs have the same locality grid? Which is the program with the best locality and which have the worst? Do you think that the design of memory system that exploit the locality of certain kind of program, which will be the most common in a system, can increase the system performance? Why? The first answer is yes. All the programs do have the same locality grade. This is because the program use temporal locality, which is the instruction of those programs have a high chance to be executed. The instruction can be fetched easily and takes no time in searching for the same instruction when it kept in the cache memory. The second answer is the program that have the best locality is NASA7, while the worst one is MDLJD. The third answer is yes, it can increase the system performance because programs with good locality tend to access the same set of data items over and over again from the upper level of the memory, ranking, and run it and make it to run faster. Then we'll go to second question. During the development of the experiment, you can observe graphically how in general the miss rate decreases as the execution of the program goes forward. Why? Explain the reason. The miss rate in cache is the fraction or percentage of access that result in a miss. It follows the hit rate plus miss rate is equal to 1.0, 100%. When a cache miss occurs, the desired address is loaded onto the system bus and the data are returned through the data buffer to both the cache and the processor. When the index was found for address which is to be accessed, tag field of the cache will be compared with the tag part of the address. The cache hit was obtained if both of them match, otherwise it was missed. The data will continue to be located in the underlying data storage when the cache failure occurs by the program, extending the length of the request. The system may write the data to the cache and the latency will be increased even though the latency is offset by the cache hits on another data. Therefore, the miss rate will decrease. This is all of my present. Thank you.
Yes, Assalamualaikum warahmatullahi wabarakatuh. Okay, today I will share to you how to use the SMT cache. Okay, first of all, we will need to open the SMT cache application and then we will configure the multiprocessor, main memory and cache. Okay, for this project, we will use SMT with number of processor 1. Okay, and then the Snoopy protocol is messy, and then for the bus arbitration is random, and then click OK. Okay, for the main memory, for word wide bit, we will choose the 16. It is already alright here, and then word by block is 32 byte, 32. So this is also correct. And block in main memory is 81. So we'll go down continue. So this is the correct one. So then we go to configure the cache. So the first one is the block in cache is in this project we will use 128. So the the cache size is 8 kilobytes and the mapping is we set to fully associative and replacement policy is LRU and that's it, and then we press OK. Okay, so after we configure the multiprocessor, memory and cache, and then we can open memory traces. So for memory traces, we can go to traces, VRG, and for this project, we will use SWM, NASA, and MDLJD. So we will first use MDLJD, click OK, and then for the we click the evolution first for the cache. You can see the graphic and the text. So for the graphic one, we first change this to complete, and then we will execute. So as you can see, the graph will be created until it is finished. So just now we will just wait for the graph to be finished, and it will be like this. So this is the graph. As we can see, you can see the graph is different for hit rates and miss rate. And this is the final right back. You can see, and then you can also go to multiprocessor to check it. So after we done with the MDLJD, we can change to NASA 7, and then we can also do same thing like before, change to complete, and then we execute. As you can see, the NASA 7 is faster, and you can see the block transfer is 56. Yeah, this is the cache block, hit rate and miss rate. So after NASA 7, we can also change. We need to untick this box. We can go to SWM for the cache. You can see same as before. We choose complete and then execute. So we will need to wait while the graph is being plotted, and we can see the axis number is increasing, the hit rates, the miss rate. We can see all of it here. So as you can see, the graph is complete. Block transfer is 12, as you can see. Okay, now as you can see, between the three memory places, the slowest is MDLJD, the fastest is NASA 7, and the second fastest is the SWN. So that's how to use the SMP cache. That's all from me. Thank you.